It's nice to be here. 20 years, a long time, and a lot's happened. And you can see from the title of this, and we're using the chart just sort of stimulating discussion and conversation more than anything else. But the main theme is about transformation, and transformation has been an integral feature of HPC for as long as I can remember. And the transformations have come periodically, in some cases very unexpectedly. I remember in 1998, coincidentally with the beginning of the SPXXL, that a number of us in IBM were sitting around lamenting the circumstance of the day. And if you can go back in time, for those of you who were around at that time, you recall that the world thought that HPC was going to devolve into Itanium and Windows, right? That's what the view of the world was. And a lot of us sat around and said, what a nightmare this is going to be. Not because there was anything intrinsically wrong with Windows or Itanium. History will make their own judgment on that comment. But because we saw it as a demise of innovation. And it was a great matter of concern for all of us, because I remember the conversations very clearly. We were talking about, we'll never let our children come into HPC because there'll be no opportunity to really do much innovation. And what happened subsequent to that? Well, you saw the emergence of the whole open source phenomenon. You saw the emergence of Linux. You saw in 1999, December of 1999, the initial thoughts that led to the Blue Gene system from IBM, which transformed the orientation in terms of design in HPC to something that was very energy efficient and really dramatically parallel in its conceptualization. So in a very short amount of time, coming, one would think, out of nowhere, all these different ideas came about that transformed the way we thought about HPC at the time. This is a natural process. Nothing someone should get be anxious about or afraid of. Transformation occurs all the time. And the motivations for this come from a lot of different angles. It can come from inside the industry as we deal with particular technical issues. So for example, the struggle that people have with where the state of Moore's law is and the benefits that accrue from that. It comes from a recognition of certain exogenous kinds of effects. Going back to Blue Gene, the proposition for Blue Gene was really centered around how we deal with the crisis that we saw emerging with respect to power consumption. And we hid the whole sort of notion under this idea of proteomics and trying to build a system to handle computing at that level of scale. But the project was really about energy efficiency more than anything else. So in 2011, and I'm vague on this date because I just can't remember anymore, we began to have discussions inside of IBM about what the next transformation was going to be in supercomputing. And the idea was motivated by the interest in going after exascale, which, of course, as we all know, is close to becoming a reality very shortly. So we were having architectural meetings inside of IBM. I was chairing these meetings with research. And the issue was, how do you build an exascale computer? Now, the interesting thing is petascale was recently achieved. From our perspective, that was the Roadrunner system at Los Alamos from an operational perspective. And that was circa 2004, 2005. And now we're in 2011 and we're wondering what's going to happen here. Now, if you looked at the top 500 graphs, you would have said, well, exascale will happen automatically. Every 10 or 11 years, you get 3 orders of magnitude. But of course, that's a simplistic way of looking at things. There's nothing behaviorally motivating by the existence of a graph that tries to extrapolate the past to the future. Humans still have to take action to realize what that future is going to become. So the fact that we just sat back and waited for evolutionary processes to take place at a standard rate would generate exascale seemed to us to be sort of a risky proposition to entertain. So the question was, what action should we take? And I asked a question one day, which was, what does it cost to manipulate a byte of data? And it's a simple question, right? And from a computer science perspective, the computer scientists get all wrapped up in, the amount of picojoules and stuff to move a bit from here to there and so on. But it was a higher level question which had at its core the notion of what is the effect of data on future design? Because if you think back to 2011, the idea that was really front and center in the minds of most people was the phenomenon of big data. Plus or minus a year or two, it doesn't really matter. But it was becoming part of the vernacular. Big data was becoming the thing to really think about and be concerned about and so on. And the question was really, if big data is the thing, just like in 1999, power was the thing, what is it that we do as designers of supercomputers to evolve in the context of that transformational kind of exogenous event? And we didn't have a ready answers to the question, but we did some investigation. There had been some work done on the Amazon cloud that gave a notional idea of what the cost was of manipulating a byte of data, or a bit of data, it turned out. And I think it was on the order of 600 to 6,000 picocents to manipulate a bit of data. Now, this was Amazon cloud, so you deal with movement from where data is stored to where data is processed and so on. But I thought it was a reasonable proxy for how we should think about systems in the future, because as data grows, the impact of latency becomes progressively more pronounced in terms of the consequences that you entertain. So picocents of data, 10 to the minus 12, seemed like a pretty small number until you began to realize how exposed we are in our industry to the tyranny of orders of magnitude, right? So, there's an English expression that says, easy to say but hard to do, right? So, we did petascale, so exascale is just, we wait 10 years and it gets done. But that's 3 orders of magnitude, or 1,000 times, right? And the tyranny of 1,000 times is quite dramatic, because if you look at 10 to the minus 12 and multiply it by 1,000, of course, you're 10 to the minus 9th. So your picocents start to get compressed accordingly, or that measure of order of magnitude starts to get affected. So when you think about moving from petascale to exascale, when you're moving from petabytes to exabytes, or yottabytes, or zettabytes, you can begin to see how these phrases that we toss around somewhat cavalierly have a material impact on what's really the innovation that's required to make the nature of what we need to do operational. So this for us was sort of a profound realization, and you say, well, how stupid could you have been? This is very easy for everyone to have seen. But think back to the 1990s, the SP system. So I was a development executive responsible for the SP system in the 90s, and I can tell you the amount of time we spent worrying about things like power and data was 0, right? Because remember, we were removed from the state of the art of where we are today by many orders of magnitude. And so the impact of things like more data or the impact of the energy consumption was not a grave concern. Back then, somebody said, well, we have more data. You'd say, well, throw some more disk on the system or something like that. Until you start to multiply things by 1,000, you see how impractical these things become. So as time moved on, we were starting to become exposed to this growth rate of requirement that manifested itself necessarily so with the way we were thinking about designing systems. So this gave rise to an investigation of what the impact of data has on supercomputing design, which is sort of what we're talking about today. I wondered where I put this. Okay. So that was just a preamble to what I'm going to say now, which is about big data, and it's about transformation, and it's about cognitive capabilities and how these things all are coming together in the next wave of transformation in our industry. So let me take you back 400 years. 1620, Sir Francis Bacon principally outlined what we think of today as a scientific method. Now, people point to that, but of course he stood on the shoulders of giants that went back another 2,000 years. So we shouldn't delude ourselves into thinking that he came up with this idea originally, but it was the way that we think about science in a modern sense to this day, where we talk about hypotheses and data, observation, experimentation, and so on. And as you all know, because you're sitting in this room, over the last 30 or 40 years, computational capabilities have really become an integral part of the modern scientific method. And it's become an integral part of the modern scientific method because there are experiments you'd like to do that are not capable of being done really any other way than through computational means. You know, when you look at the evolution of climate change, for example, over 100 years, or you look at trying to secure the safety of nuclear stockpile, things like that, things that either take a very long time or that might be very dangerous. If you try to use conventional methods, the gravitational pull of using simulation and modeling becomes a very important feature for how we want to do science going forward in time. And you know, with respect to what we've been doing for the last several decades, there have been massive improvements in terms of computing and architectural design and so on that have really focused on amplifying our capability to do simulation progressively faster, more effectively, and so on. So we've you know, overcome issues of scalability. Now we're talking about millions of core systems. And back in 1993, you know, we were struggling with the idea of having scaling up to 500 nodes or something like that. So we go way, way beyond where this all started back 25 or so years ago. So a tremendous amount of activity in this area that are the byproduct of a lot of people in the industry and to which we've all, and mankind has been the beneficiary of, right? And you can see this by a variety of papers that have been published, how the application of simulation has really evolved in such a way to take advantage of the innovations we've seen in computing over the last couple of decades to produce some very interesting results. So we've got petascale. This is an example of discovering new electrolytes. You see the number of threads on the bottom getting up into the millions, runtimes decreasing dramatically. You look at cloud cavitation, collapse bubbles, and you see the kind of efficiency that was generated in this particular case, 73% of peak performance on a real application, not LinPack. And then you look at things like implicit solvers and scaling those to dramatic degrees. And so this is all public information. These are papers that have been published or won prizes and so on. But the problem is complexity is not that understandable with just brute force approaches. And frankly, simulation has evolved along more of a brute force paradigm than anything else. It's been a common technique that's evolved taking advantage of more and more compute capability, and that's kind of it. And things are changing. We know this, right? So let me give you some perspectives on how things are changing. When we think about HPC, what do we mean by that? Well, the classic marketplace data suggests that HPC is characterized by an amount of dollars invested on an annual basis, right? In 2017, that number is $11 billion. That's for servers. There's an incremental amount of money for storage, software, and services, maybe another $6 or $7 billion. And you look at that $11 billion and you say, what is that? And it turns out that while we weren't necessarily paying close attention, something's been going on, right? That $11 billion has been split in some very interesting ways. And one of the interesting ways is that about 20% of that spend rate in 2017 was dedicated to big data analytics and cognitive. All right? So think 2.3 billion subtracted from the 11 is now big data and cognitive. Oh, well, that's not simulation, that's something new and different. So there's sort of this undercurrent of transformation going on by virtue of observing the way people are spending money, and they're reacting to the circumstances around them. What's been going on? Of course, the phenomenon of big data, so we need big data analytics. What else has been going on? The emergence of machine learning and deep learning in the last couple of years has been going on. So people are beginning to experiment with this, and they're spending money accordingly. Now, the interesting thing about these numbers is that $2.3 billion is growing at greater than 20% compound annual growth rate. And if you subtract that away from the growth rate attributed to HPC in general, classic HPC spending on simulation and modeling is around 1% a year. So all the growth rate's been driven by the embrace of other kinds of approaches being integrated into classic HPC. And this is not remarkable, right? Transformation is a byproduct of what we've been doing from innovation for a long time in this space. And it's something that reacts to, as I said before, either the stimulus of constraint within our industry, think Moore's Law, but also the imposition of factors from outside the industry that require reaction. And so as simulation has evolved through brute force methods, people are beginning to experiment quite directly with the incorporation of other techniques to provide greater and greater insight. So you all know this chart. I've produced this chart for probably 6 years. It's always looked the same. It always shows us being where we are. It always shows this tremendous growth over the course of time. And all we've done is continually shifted the date on the right-hand side. All right, so the nature of the curve hasn't changed. We've just shifted it in time. And of course, you can see on the right-hand side all the different things that are contributing to this growth rate of data and how we deal with it. And if you think about big data, it's evolved in terms of how we even think about it, but now we're really talking about it in terms of this multimodal context, full contextual analytics, and so on the extreme right-hand side, where it's not simply a large amount of data the way we always used to create data. It's unstructured, it's structured, it's audio, it's video, it's relationships, it's risk, it's all kinds of different kinds of attributes you see embedded on the right-hand side. So it's not only the volume of data that's growing, it's the nature of what this data looks like and the form that it takes and the relationships it characterizes and the sources from which it emanates, right? And so when we think about taking a more holistic approach to this whole idea of scientific exploration and modeling and simulation, we think that the next revolution is really the inclusion of cognitive techniques in classic simulation and modeling to provide different kinds of insight and different levels of understanding than the simple brute force method of simulation would provide. So what's the point? The point is our language is corrupt, and it's corrupt in very interesting ways. We talk about HPC as if we know what it means, but we also use HPC to tell people what it's not. And the problem with telling people what it's not is you deny yourself the opportunity to take advantage of innovations that come from outside your domain of expertise. And so the argument of what I'm trying to make today is that the barriers that we create, and IBM is as guilty in this as anyone, of compartmentalizing different kinds of technique, science, activity, and so on, is itself a limiting kind of construct that gets in the way of true innovation. A small aside, in IBM, when we come up with a new idea, the first thing we do is we create a business unit to drive it, right? Now, that's interesting from an organizational science perspective because when you create an organization to do something, the organization has two goals. One is to do what you've assigned it to do, and the second thing is to exist and to continue to exist. Why is that? Because humans are involved. They get titles, they get promotions, they get compensation. And if that mission were to suddenly evaporate or change, all those things would be taken away. So how ideas come to fruition in industry is interesting, not only in terms of the technology, but in terms of how organizations evolve to make the technology come available and what the consequences of that are. One of the unintended consequences is that you set up barriers on an organizational boundary that essentially precludes people that exist within any of these organizational hierarchies from paying attention to what somebody on the other side of the room is doing, or the other side of the world or the other company and so on. And it's a very unfortunate circumstance of how businesses get constructed and how ideas are pursued. So, for example, in IBM, you'll hear about people saying, well, I'm part of the HPC organization. Somebody else will say, I'm part of the Watson organization. Somebody else will say, I'm part of an analytics organization. The question you should be asking is, do you guys know each other? Do you talk to each other? Do you compare notes? Do you integrate your ideas in any useful way? And I think that's a struggle any institutional company, enterprise, and so on suffers from in terms of risk. So we observe this, and we're trying to break down these walls now. And so for us, HPC is not something that we define in sort of the classic way that says it's only simulation and modeling and that's it. No, it's these new ideas that are getting integrated into HPC in a variety of different ways that are forcing the concept of HPC to be transformed for good use. And remember, transformation, my thesis is that it goes on all the time and we have to embrace it. So what are we saying? We're saying brute force activity has gone on to drive simulation. That's good. We've got dramatic scale. We've got all sorts of interesting benefits and byproducts from that. Big data has come along, presenting us with issues in terms of how we simply handle it and how we design for it. And the nature of the data, coupled with the evolution and the innovation that's come out of the artificial intelligence community, suggests this wonderful confluence of trends and events that if we could only make them come together, might give us something really quite spectacularly different than what we have today. So, this is all a recipe for the potential for disruption. Our focus historically has been on the right-hand side with simulation, but what are we doing about evidence and experiments? What are we doing about knowledge? And suddenly you look around and you say, well, we've got this multi-contextual data, we've got AI, we've got these other capabilities. Can we bring these all together? Can we disrupt the market the way we know it today to take advantage of these evolutionary ideas? And the answer is, yeah, the way forward is something that we call cognitive discovery, where we'll still put a focus on inference and simulation, but we'll couple it with AI techniques that fall into the categories of knowledge, evidence, and experiments to bring data together in interesting ways to create benefit that could not otherwise have been realized. All right? So this is the amalgamation of big data, artificial intelligence, simulation and modeling in an evolved construct of how we pursue science and engineering to create greater value over the course of time. And it begins simply by data, right? So IBM has I'll call it a tool for lack of a better word, called document ingestion, PDF ingestion. This is a fundamental starting point, right? So before we jump to thinking about, neural nets and training models and things like that, question should be, and the data comes from where? What does it look like? What does it embrace? What does it talk to, et cetera? And you start by finding some way to ingest data. Now, it turns out the PDF ingestion tool is pretty effective. It can handle handwritten notes. It can handle mathematical formula, chemical formula. You can do all these things to create a corpus of knowledge which can then be evolved into creating knowledge graphs. And the knowledge graphs begin to show relationships and are susceptible to things like deep search to give you progressively greater and greater insight around this corpus of knowledge that you have. By the way, the document ingestion is quite critical because although we like to think about data as being amorphous and just sort of out there and something to be collected, remember in the context of a particular institution, the data might be secret. It might be something that's not public, that's only available internally, that you want to capture and you want to retain for a lot of reasons. If you think about the Accelerated Strategic Computing Initiative that began in the early 1990s in the US, which now, of course, today has changed to ACM and is the sort of organizational focus that's given rise to the Coral systems and so on, the initial motivation for the ASCII program was capturing the knowledge of the physicists who were getting older, retiring, and dying. Right? That's what the initial motivation was. That is the message that was delivered to the US Congress that said we need to start this computational science program in the Department of Energy because these people and their knowledge are going away. They're evaporating. So where else is this true? Well, it's true everywhere, right? You're always going through transformations in your institution about people leaving and taking institutional knowledge with them. And now finally we have techniques and tools that allow you to begin the process of capturing that data, but not only capturing it, making it a foundational element for what you want to do computationally to take advantage of that. So, how do you build a simulation? Right? Well, you review the literature, you talk to your colleagues, you review your own history, and what is that other than trying to build on top of a corpus of knowledge that exists in a very unstructured way generally, which now is subject to having tools available to put more structure on this and allow us to really pursue it. So you can follow this up. We've left the top of the pyramid open, shall we say, just to indicate that there's always the utility of having humans to participate in this and to really orchestrate everything that's going on. So you can do all these things, but you really can't do them that effectively without humans to be involved. So we go from knowledge extraction representation, we do the inference-driven simulations, we finally conclude with automated technical reason, and then we apply judgment on top of this to take us where we want to go. Here's an example. I guess the backdrop doesn't show up very well, but this is a material science problem. So as background, we have since 2015 been running proofs of concepts around the world in a variety of application domains to explore how this notion of AI and classic simulation modeling should come together. And this is a classic example of materials discovery. These, by the way, are all based on real customer engagement, so I'll give you a brief outline. I won't tell you the customer. But the circumstance is this. This is a company that invests in a lot of research for new materials, and they find themselves falling behind because they're being tracked with close copiers, principally from Asia, who are sort of ingesting what these guys are doing on the research side and creating near comparable kinds of products with very little gap in time. So you make an investment, the investment might go on for 5 years, you introduce a new product into the marketplace, and before you know it, maybe 6 months later, somebody comes out of Asia and has something that looks pretty much the same, but at a much lower price. So they've leveraged your investment to take away your profitability. And the company sits there and says, well, how do I compete? Because I can't change that phenomenon of the marketplace. So the only way to really compete is to dramatically compress the amount of time involved in generating new materials. So the classic way to do this would be a literature review. It's non-scalable, human-based outsourcing, et cetera. You would do simulations. It would take months to do it. You would do analysis to confirm the simulations. There'd be a lot of empirical tests and so on. It takes years. Well, now you apply this whole notion that I alluded to initially in terms of starting with ingesting the data. Here you see a paper out of the literature, and then there are mechanisms that you see related across the top that put this into a form that actually can be operated on. So this is a big deal. Now, it's not as sexy as somebody saying, oh, look at my distributed deep learning model and what I did with it, and let me show you how I invoke GPUs and all these other things, and look how fast I made it run. But you know how much time is spent on that compared to this? Well, from a data science perspective, before you get to the point of training models, you spend 80% of your time worrying about acquiring data, organizing it, making it available, and so on. So if you think about having just a singular focus on the model, you may progressively over the course of time find yourself more and more working on the margin, right? So if all your effort is spent working on 20% of the problem, at a certain point in time, somebody's going to say, what about the other 80%, right? So that's why things like this are important. Now this feeds into the ability to create knowledge graphs and so on. You can do deep search on it. You can start feeding it this in to the neural net models that you're building and so on. And you can take this down, and this happened to be alloy design, and we compress this notion of years actually down to weeks. So this is now implemented by this company, and they find it to create a strategic advantage for them with respect to the competitive environment they were in. So they found a pathway to effectively defeat the fast follower by virtue of using these computational techniques coupled with these AI capabilities to dramatically to improve the nature of the simulations being produced, but also in terms of creating dramatically improved insight by virtue of the magnitude of the information they were able to integrate into the problem. Now, for some people, of course, alloy design is somewhat removed from day-to-day life. So let's bring things a little closer to home and talk about shampoo, right? So everybody's interested in shampoo, or their wife is interested in shampoo, or somebody in their family who has hair is interested in shampoo, right? And ask yourself, how do you design shampoo, right? Well, it's a chemistry problem, right? It's a problem in formulation. And you have inputs that you want to mix together, and you want that mixture to have certain attributes. One attribute is you don't want those different elements to separate in the bottle. Now, you have this with salad dressing in the store. You may go and see that, and you say, well, it's different layers, and it says shake well before using, and you mix it up, and you get your salad dressing. The guys who manufacture shampoo don't want to really tell you to do that. They want it to be mixed, they want it to stay mixed, they want it to behave in a certain kind of way. So, how do you design shampoo? Well, as a problem in formulation, you can begin by setting up a standard wet lab, chemistry wet lab. You hire a bunch of scientists, and they mix things together, and they have a hypothesis, Francis Bacon, right? They make observations, they do measurements, they either modify the hypothesis, they modify the nature of what they're looking at, but it's an evolutionary process that takes place in a relatively serial kind of fashion. It takes money, time, et cetera. Remember, time generally, since you're all in the HPC business, is the enemy of everything we try to do. It's always faster and better, faster and better. So you could do it that way. Or you could simulate it, and simulations of the problems of formulation have been done. This happened to be a problem that we ran out of STFC in the UK. I won't mention the company, but STFC has a program called DL Poly that they use to simulate these kinds of formulation problems. So that was good, that was progress, but it still took time and money. So what we did was we applied machine learning to the process. And we said, all right, wet lab, okay. Simulations, okay. What if we now incorporate artificial intelligence techniques on top of this? So we applied Bayesian optimization to the problem of the simulation. So you have ensembles of simulations. You look at Bayesian optimization as a way to choose what the next simulation is. And by virtue of doing that, we found out that we could reduce the number of simulations by 2/3, right? And increase the resolution by 4 orders of magnitude. And you know what this has nothing to do with? It has nothing to do with Moore's Law. Nothing. This is all the integration of new techniques, software, and the amalgamation of approaches in a way to provide insight and benefit that the classic expectation of brute force simulation would never provide for you, right? There's nothing to do with Moore's Law here. In fact, you could say this is one of a million examples of what you need to do in a post-Moore's Law world, right? Quantum would be another example like that, right? There are a whole category of approaches that one could begin to apply here. This is implemented now by this company. It's a consumer products company with dramatic increase in their ability to solve, and believe me, they're producing more than just shampoo. They have lots of formulation problems. But as a general technique, this has proved to be of dramatic value to them in terms of compressing time or compressing the amount of compute resource and providing greater insight than what they would have had ordinarily. So we've run probably 25 different engagements like this around the world in all kinds of industries. We've done ball bearings, we've done oil and gas, we've done applications in the finance sector and so on. And you see this over and over again. The explicit incorporation of AI methodologies, coupled with what we're doing in the standard practice of evolving our capability in simulation and modeling, is producing extraordinarily positive results compared to what we would have gotten had we not brought these ideas together, right? So we have the ability now to ingest huge amounts of data and organize it. We have the ability to apply deep learning and machine learning techniques on top of this. And we have the ability to couple this with the way people do simulation. So imagine now the following. When we think about the relationship of AI and HPC, we use AI to build better simulations. We use AI to run the simulations better, in this example. And we're going to use AI to interpret the output of simulations in ways that people didn't anticipate before. And all this provides tremendous benefit that if we stayed to our roots and said, well, HPC fits in this very narrow category and AI fits in a separate category, these kinds of benefits would have been elusive to us and denied us. One can implement this in a variety of ways. I don't actually know how this chart remained in here, but this is an example of the architecture that we're sort of a reference architecture that we have to make these things come together. So it presumes, first of all, if you look on the bottom, a whole variety of different kinds of hardware platforms, right? It doesn't say, well, this only works on platform A and not platform B. The harsh reality of life is this. Most HPC applications run on x86, and it also is a harsh reality of life that AI applications run best on power architecture. So bringing these two ideas together is natural. And in fact, it's itself a transformation of the way people are thinking about acquiring systems. Until relatively recently, people said, well, I'm an x86 shop, so the only thing I want to talk about is x86 technology. But I think NVIDIA actually did the industry a favor by virtue of DGX and so on to demonstrate that there's value for other technologies, purpose-built systems, if you will, and people have gravitated to that. So it's no longer a foreign idea for people to have a DGX, a power architecture, an x86 architecture, an ARM architecture, all working in the same environment if they're particularly suited to the purpose to which they're being applied. So anyway, you have a variety of acceleration that runs on top of this. We're not going to be dogmatic and say there's only one way to do this. Linux becomes a key, and then you have a complete software stack that brings you right up to the application level. That includes, by the way, things that help you do more in terms of managing data than the example I gave with PDF ingestion. So you see Conductor with Spark. You see a variety of other things here as well. And at the end, what this results in is a transformation that I've talked about today in terms of how we're doing computing that I think will cause us elation by virtue of what it's able to produce, and also some concern in a pragmatic way. So let me, if there were a soapbox, I would stand on it for a second. It is remarkable to me, but not surprising. But it's remarkable that when we talk to people who use HPC systems, by and large, they understand this. Why? Because as I said at the outset, more than 20% of the spend rate is now going to data analytics and cognitive approaches out of these HPC budgets. So they understand it. And yet, what do the RFPs look like? Yes, we really want to have this all together. By the way, can you run LinPack? What does LinPack have to do with Bayesian optimization as applied to a problem in shampoo formulation? Nothing, right? And so unless we begin to take on the historical attitudes of how we value HPC, we're going to retard the progress that's available to all our clients accordingly. And it's a simple fact. And I will tell you this, and I won't mention the customers or anything like that. But there are major customers in Europe over the last year who have found themselves in the following trap, where they've embraced this idea of what we've talked about today in terms of big data and analytics and AI, and they've written RFPs in a classic way, and they've bought systems in a classic way that have denied themselves access to the ability to do big data, analytics, and AI, and their customers are not happy, right? And they don't know what to do. So, with apologies to Jack Dongarra, I think we have to fight the battle of overcoming the tyranny of top 500. Top 500 has resulted in certain ways in a retardation of innovation in terms of the kinds of systems that are being produced, because it's rather easy to build a top 500 system. It really is. Oh, more floating point, bigger SIMD unit, got it, go, run LinPack. Oh, by the way, how efficient is your application run in that system? 7%? What did I just do to you? So I sold you a system on LinPack, and I'm running LinPack at 75% efficiency, and your applications are running at 7%? What did I just do to you? And as a buyer of products elsewhere in your lives, how is this reasonable? How does anybody look at this and say, oh, that's a reasonable way to buy stuff? I think it's indefensible. Sure, people will say, yes, but I run LinPack to see the energy consumption and so on. Great, then do it. But don't buy your system based on LinPack alone, right? Don't bias it by that. We've had situations in the last year where customers have said, yeah, I really like this, we really need to have this, but we want you to run LinPack anyway. I said, well, I have to put in another $5 million of hardware to reach a LinPack number, which, by the way, is unrelated to anything you're doing on a day-to-day basis. Do you want to pay $5 million more just for that benchmark? Apparently, people do. Apparently, people actually don't understand what they're doing, though. So I think that as time moves on and people become more comfortable with the nature of how these different ideas need to come together, I think you'll see a real struggle with this whole notion of top 500 and LinPack, HPL, and all this stuff as a criteria for choice, and they'll have to find other ways to make their judgments. Now, the Coral systems, by the way, which I'm happy to report are well along the pathway of installation and customer acceptance tests, the criteria for choice for that contract had nothing to do with LinPack. It was all based on application performance. What a novel idea. What do you do on a daily basis? I run applications. Therefore, I'd like a system to run my applications faster. Makes logical sense, as opposed to saying, what do you do on a daily basis? I run applications. How would you like to buy your system? On a benchmark that has nothing to do with the applications I'm running. That seems like an odd idea. Department of Energy is not composed of odd people. They're actually very thoughtful people. And so when the criteria, through discussion over a sustained period of time, was conducted on how the Coral RFP was to be run, it was based on application performance. That may be elusive to a lot of people, because certainly these are big systems and LinPack numbers will be produced and so on. But the selection criteria had nothing to do with LinPack. What a novel idea. Why don't we buy systems based on what they're supposed to do as opposed to a benchmark we're supposed to run? One last historical footnote on that. In the early part of the last decade, as people were beginning to talk about petascale the same way we were talking about exascale today, although back then it was about petaflops, right? We've at least made the transformation that people are talking about exascale and not exaflops. There was a senior executive in IBM who said, well, we have to be first. And I said, why do we have to be first? Because, if I do a petascale system on Monday, on Tuesday, somebody will come with a 1.001 petascale system. And so, what's the point? And I said, oh, by the way, given that we're talking about petaflops, what prevents the Riken Institute in Japan from getting a whole bunch of grape cards and trying to do something to enable it to run LinPack, and then saying, oh, look, we got a petaflop. Isn't this great? So the idea of the semi-insanity of pursuing this is not a today kind of thought. This has been around, at least in our minds, for probably 10 to 12 years. But it's incumbent on all of you, because some of you are consumers of HPC, some of you are providers of it. But it's a very dangerous pathway that people continue to pursue. We all understand the reasons why. The funding agencies get turned on by somebody saying, look, I've got the fastest system in Europe or something like that. Well, somebody's going to say, who's got the most effective system in Europe? Somebody's going to say, who's got the biggest AI system in Europe? Who's got the whatever system? And everybody should be prepared to answer those kinds of questions. So that's all I wanted to say today about this. The transformation is upon us. It's not something I wish, it's just something that's coming that we have to be cognizant of and take advantage of. And these ideas of big data, AI, and HPC cannot be separated. They're all part and parcel of the same thing. And you have to look at system designs and the evaluation of systems to look at how these things are dealt with in a composite form, because that's where value to clients will eventually come. So that's it. Any questions? Yes? Yeah. Yeah, I think there are a lot of drivers. This talk wasn't meant to cover the whole dynamics of what's transforming in the industry. But I think that, think about the language you use. You talked about silos, right? That's another issue that the industry is sort of dealing with right now in a lot of different ways. So, by the way, the chart I showed here was sort of an attempt to sort of get away from that issue of silos by saying you have these disparate kinds of hardware technologies, but they can all be managed under a common kind of umbrella to facilitate the movement of work from one architecture to another, if you want to think of it in that fashion. The existence of container technologies to facilitate that, and the other kinds of things we're talking about are all there. It's an attempt to kind of break down the notion of silos as discrete, separately managed, separately controlled kinds of entities, and a way to try to bring them together. There is no recipe for the best way to do that, right? There's experimentation that's going to go on. There'll be examples coming out of the marketplace that'll give way to best practices. Example, there is a retrenchment from public cloud in HPC. I mean, people have talked about the wonderful benefits of having Amazon and Microsoft Azure and so on. But if you actually look at the data, the transformation that's going on in cloud and HPC is more on-prem, and it's caused by issues of data security. By the way, the cost of cloud, I have customers in California that are paying $8 million a month just to manage data movement to and from the public cloud, which to them is like, how are we saving money? What is going on here? $8 million a month? So I think there are a lot of things that are shaping this. And I think that what I tried to outline were broad ideas. And I think that the marketplace will experiment with these, and over the next several years, best practices will emerge, and we'll move on, and we'll make that transformation as well. Other questions? Yes? I know.
I mean, that's the biggest problem. If we are still taking the top 500 as the valid
Yep.
for evaluating the work and getting money. So we're like in a loop, and nobody knows how to get out from it.
Yeah. Well, I think that is the problem, right? The funding agencies are not very sophisticated. They're just providing money. And you impress upon them by making a declaration that you're going to be first, best, biggest, whatever, right? And the way you point to it is to say, look, there's this published document that says top 500, so look where we stand. And there's a benefit to that, right? But I think the transformation of HPC systems is simply forcing a conversation that needs to be had about other ways to make the evaluation. The Coral system at Oak Ridge is the biggest AI system in the world. Or just count GPUs, right? And we'll do a measurement based on that. I'll take distributed deep learning and scale it up to thousands, 20,000 GPUs, right? Is that a new measure that you want to entertain? Is that a measure that you want to say is characteristic of what my AI capability is? I don't think people know at this point. They don't want to get trapped in that same simplistic notion. There's an analogy in quantum, right? Today people say, well, how many qubits do you have, right? So that's a measure of what your quantum capability is. Completely false. IBM introduced about a year ago this concept of quantum volume to demonstrate, and by the way, this paper is public and people are commenting it all the time, that if you just focus on qubits without focusing on communications and scalability and error correction and so on, you don't have much of anything, right? So there is a natural human tendency to gravitate to a single figure of merit, to say, yes, here's a order, I'm number one, you're number two. The companies in our industry are behind this because our marketing people like to say, oh, look, we're number one, right? And so if I'm number one, you should treat me with greater credibility. All I'm telling you is I don't have a solution for it, but it's extraordinarily stupid, right? You would not buy a car this way, right? If let's assume you have a BMW, right? And the speedometer goes up to 200 miles an hour. Do you ever drive 200 miles an hour? No. But does BMW put their car on a racetrack and say, look how fast this car goes, right? You're never going to experience that in your lifetime, right? And yet, are you influenced by it because of that? Maybe a little bit. It's a really dumb idea. Because if it's 200 miles today, are you going to be more impressed if I show you a car tomorrow on the racetrack that can go to 220? You're going to say, oh, well, now you're faster on the racetrack. You're faster on a performance metric that I'm never going to use in my life. So I'm going to pay more money for the new car because you're at 220 and the old one was only at 200. And meanwhile, I have to drive at 55. No, I mean, there's torque, there's horsepower, there's braking time. There are a lot of features here. I mean, it does you no good to say I can drive 200 miles an hour and my brakes will not stop me in anything less than 800 feet because you're already dead, right?
Now it's a time of the top 500 to start adding these categories, not only limiting it to limback. Just now we have other categories where they have to drive that to be able to make it more and more realistic and closer to.
Well, maybe they have to drive it, maybe somebody has to drive it, maybe we all deserve some responsibility here. If you note, IBM has not made any marketing commentary about top 500 for probably 5 or 6 years now. And we've not attacked the top 500 organization. We've simply said we're not going to play this game. And some people have said the same thing and others have not. It doesn't matter. At the end of the day, what you need to come to grips with is how do you provide value to the users of HPC? And if you delude people into thinking that, well, I've got this wonderful LinPack machine. By the way, how many of these machines run at full scale all the time? Almost none. What you do is you get a big machine, you get a benchmark, and then you partition it up, and you say, today you've got 4 nodes. What the hell does that have to do with LinPack anymore? I'm working on 4 nodes. So craziness is afoot, but that's okay. As long as we know it, we can start to react to it and so on. But my message is simple here. be thoughtful about what you do in the light of what you're trying to accomplish scientifically. And don't get deluded into these artificial numbers and think you've accomplished something when in fact you may not have. That's all. Any other questions? I think we're almost out of time. Yes?
I also see the benefit of the cognitive extension. And at the moment we are GPUs for that, so GPUs we can use it for double precision, number crunching, and for cognitive stuff.
Yep.
But I assume so the whole area of deep learning, cognitive AI is so huge.
Yes. The amount of money flowing into these startup companies to create dedicated hardware for AI is dramatic. And it's all over the world. Look, for example, in California, there's a company called Esperanto, which I think started the year with maybe 20 people. By the end of the year, they expect to have 150. They're trying to do a RISC-V implementation of an inferencing engine. Okay. And then, you know, that's just one company. There's dozens of these companies. The other area that's quite interesting right now is the amount of money flowing into quantum startups, trying to do things in that area as well. Because remember, this is transformation today. What's the transformation tomorrow? Neuromorphic, quantum, all these other things are coming as well. So there's a huge amount of money flowing into all these areas right now to create you know, these more custom kinds of approaches. It's an interesting experiment in the marketplace because if you look at NVIDIA right now, which is doing wonderfully well with respect to GPUs as applied to cognitive approaches, that's a classic economic recipe to invite other companies to come in and to try to compete. Now, NVIDIA is a big company now. They spend a huge amount of money on R&D. They're wildly successful. So I would expect people to come at them in unorthodox kinds of ways. In other words, don't try to build another, you know, Volta. You're gonna have to build something different price point, different approach, different kind of problems that you're solving on. But this is all coming. And I think you'll see stuff coming into the market this year and next year with a vengeance. Okay?
Thank you very much.
Thank you.